Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we'll get started now. It's my pleasure to have Professor Junryo Song from KAIST. KAIST is in Daejeong in Korea. And Professor Song actually spent a number of years before he was at KAIST at IBM TJ Watson. And he's going to be telling us today about some interesting applications that he's built, context applications using wearable sensors and sensors in the environment. Thanks.
So part of the work is quite getting old now, but I pack it up to present potentially everything of what I have done, have been doing so far. So it started around year 2006 6 or 7, and it's continuing until now. So we have been developing a platform for mobile platform to support context-aware applications. So context-aware applications is good, and I believe it's a future direction of mobile applications. However, the problem is that it's difficult to develop. Okay, first of all, it's complex. Okay, sensing, feature extraction, recognition, and all those things. The problem here is that usually, I believe. Average developers are not good at those. I mean, it should be those who know some about machine learning or pattern recognition things. So it's not common yet. Right? That's one thing. And second problem is it's computationally heavy. Right? And the third, it's if it is mobile and then it also if we use a very limited sense devices, then it's resource and energy limited. So we have two problems: complexity in the logic and complexity in the environment. Okay? So we wanted to provide developers with a platform that include effective runtime environment as well as is to use APIs. And I recently saw the presentation from MSL as well. So somewhat related thing in this year's census. I was also there to present different thing. So the key building block of context-aware application is, of course, context monitoring. Okay? And this is common to many different applications. So it is good to know that it is key building block. However, it's again complex, multi-step continuous processing, and it should deal with multiple sensors, multiple devices to get intelligence. So we use built-in sensors, and we use body sensors. We also use spade embedded sensors to get the most of what we could extract. So look at the problems, the challenges here. Yes?
What is pan scale?
So personal area network. So that's what I'm saying. So it includes built-in phone sensors and on-body sensors and personal area sensors. Okay? So we support dynamic system to get connection to the sensors. In those three steps. And so here is the phone and the sensors and applications. Okay? So this is a reasonably good system. However, it is still small. It will get better. And we have a number of sensors. We can use a number of sensors, and we should also support a number of applications here. The one big difference is that, again, we should not only support application by application. If it is platform, then it should support multiple applications at the same time, I believe, right? So that should be the platform. Right? So if we think about multiple applications at the same time, then here, in fact, scalability problem occurs because the system is rather small scale. The hardware is rather small. So even if it's not that serious system as in what we see in the internet, still considering the resources here is getting quite complex. The further problem is that sensing should occur continuously, and thus all the computations following should occur continuously, and it will complicate the problem further. Right? We have naturally scalability problem considering the resources and energy problem, and also once we say that multiple applications run at the same time, we should do resource coordination, resource management, because the current way of developing applications using this kind of sensors is rather ad hoc. It's done from the application layer. So we are providing APIs to applications so that the application developers just use that high-level API and don't care about what's going on underneath. And also the system provides abstraction to the hardware sensor devices. Yes. And in the middle, it should do a bunch of things. So these two things are what I will talk a little bit about this, but rather on the second one. Okay. I planned to talk each of those bit by bit, but I don't think I will have enough time. I'll probably stop around there. Okay. So CMON. So again, we provide very high level. I will go very fast about this, but the users are given a query language type of interface. The developers, so that they can use this to specify their request in a declarative way, using high-level representation. So context is, for example, represented in this way: activity is running, and temperature is hot, and humidity is wet. And this one says alarm from false to true. So it means that they want to know. The program wants to know if this condition is getting satisfied. So it wants to know the change, not the context value itself, because it is important because it's rather event-based system. So what the application usually do is not to know. It's more to know the changes so that it can trigger the services, right? So we included that as a part of the language, and the duration specifies the time. So given this high-level representation, we do translation. So this is data structure in the system doing the translation. We have context translation map. So all these provides the mapping. So the result is something like accelerometer 1 Y value, Y energy value is something larger than 52. And accelerometer 3 XDC is less than 500, etc. Okay? So the good thing about this is once we have this representation, this one has lower level, medium level representation. For example, it has we mapped the high level representation toward those including the resource information here. Right? So we have sensor information here. So from this, we can do system optimization to some extent. So it's just like compiler we use. Right? So one example we do is that from that medium-level representation, we can extract what are really the information, the sensors we should use, and what are those we don't have to use. Okay? So here we did things like short circuit evaluation, so that if we are given this kind of queries, like is the weather hot and humid, then, and let's say we know that it's already hot or humid. I'm sorry, the other way. If it is cold, then we don't have to know the other one, right? So in that way, we can identify what are the sensors we don't have to use, right? So we do evaluation on those. So what we do is that let's given a false context, a complex false context, then we can identify what makes them false, right? And then we don't have to worry about all the other things until something comes to true, right? Yeah.
So for more complex data types like video and audio, how do you do the translation into the
No. Video, I don't. To be honest, I think video is quite different, well-studied type of sensor. Right? So we can do to some extent if we really dig into the different parts of the video encoders and decoders, right? But I'd rather say it's usually considered as a canned system for me. So it's rather, I would exclude video, but I do some of the sound. But in that sense, in the sound as well, if we do the regular sound recognition, I would not be very much interested because, again, it's a very well understood process. However, if we use part of it, for example, let's say if we want to understand who is there, are they a man or female, or are there how many people are there? All those things are variations of those, and then we can use part of it, I guess. This kind of idea. So the reason the reason I'm saying that is that whatever I do, there will be better ways of doing it, which has been already developed, if it is the regular processing. Okay.
So accelerometer seems a little bit like that case. Did you guys go in and sort of inspect that by hand to reverse engineer how it maps to the lower level?
Yeah, we did. Yeah. But it's not easy. It takes a lot of time for students. However, it's relatively easier than doing that with video. That's what I'm saying. So anyway, I will just go briefly here. The high-level idea is that once we know this is false, and we don't have to turn on all the sensors, we can extract the number of the sensors which we don't have to worry, right? So that's one idea. So here we could save about half of the sensors, and the reason for that is think about the context, the situation. Let's say there are tens of sensors questions from the applications. Then how many of them will be true at what moment? I think it should be just small. Because, for example, let's say there are tens of questions about the locations for like 10 different location-based applications. And it can ask if I'm in this room, if I'm in this building, if I'm in this area, all different kind of questions. And also there could be many ones, but I believe not too many of them will be true because I'm in a certain situation. Right? So many of those will be false. So even if there are a number of context monitoring requests, the number of those which is true at the moment will be quite limited. Right? So this heuristic really worked out, and we could save a lot. And the second idea we developed was, so here we are dealing with multiple questions at the same time, right? So we could do optimization considering all of them together. So we developed a shared processor as well as incremental processor from some heuristics of the requests. So again, this helped us to improve the performance at the minimum like 3 or 4 times in the CPU time-wise. Okay? So those were the first round ideas we developed, which has been quite old. Now once we had that, the second question is, again, if we run multiple applications, then at the same time, then we should do further. Let's look into a little bit more about the environment. So here we have a number of applications which share scarce resources of the system. And so, for example, this Mikazi mode, which is quite old now, but anyway, that can run even less than 1 FFT, even if it is lightweight. Right? So it's very limited, and we are considering running multiple applications. It's problematic. Right? And also, it's dynamic. Users are moving around, so we should identify sensors at runtime and dynamically and connect to it. And applications will come and go. Right? So one is that resource scarcity and energy scarcity, and also we have dynamics of the system. Okay? So applications cannot do it. See, it's not the matter of difficulty. To run at the same time together, sharing the system, applications should know what others are doing. So we should provide system support. Right? But the problem was that in this kind of environment, we didn't have that kind of support. Right? So we designed a system to help it. So briefly saying again, so current system, everything was done in the application layer. They specified low-level resource status or resource requirement from the application layer, and the system just receives and do it if it can do. Right? So here, the system specifies, again, the high level, the application specifies the request in high level. Right? And the system receives it and translates it, investigates it, and analyzes it, and identify what are the resource requirements. And he also understands what other applications are doing and what the system has now, and does the resource binding at runtime dynamically. Okay? So the system should provide holistic view of the applications and resources. So the key idea here is that we are providing high-level representation, APIs to the users. For example, if somebody is running, and there are many different ways to identify that fact. There are two levels. One is the sensor level. We can use different set of sensors to identify if the user is running. And the second is we can also use different logics for it. Right? So we use that alternative resource usage and logics to provide different plans to the system. Right? And so sitting in between the applications and the resources, the orchestrator has the holistic view of the system and understanding on the system as well as the application, and use that flexibility to orchestrate the whole system. Example again is that, so we have, let's say, have application A and B, C. Application A is translated and the system prepares two different plans. Okay? Application B is translated into 2 different plans, and C to 3. Okay? Among those 7, so for each plans we have, so this plan B1 uses accelerometer on the wrist, and it also, in more detail, it also has the different processing methods. So in this case, it uses frequency domain, feature extractor, and decision tree, and all these are done on the mobile side in this plan. And in this plan B2, It uses accelerometer attached to the belt, in this case, and uses statistical feature and a decision tree again. However, in this case, the processing on this part is done on the sensor, and on the mobile side is only the classification is done. Okay, so this way we can select different node, different processing method, also different use different do the computation on different parts of the system. Okay? So also we have resource demand map. Okay, analyzing the plans. We prepare the resource plans, the demands, the CPU and bandwidth and energy, etc. And the system at the background prepares the availability map by monitoring. Basically, the system undergoes continuous system monitoring to abstract what's available now. So it has CPU, memory, bandwidth, and energy in this case. And comparing the different plans against what is available now, we can select what are possible. For example, we can have this one is available according to the what we have on the resource side, but probably this is not. Okay. We further on developed a framework to define and enforce different policies. Okay. For example, the one policy can be maximizing the number of concurrent applications. Okay. In that case, we translate the policy and enforce it on top of this constraint matching. Okay. Another can be optimize the energy usage. Okay. So we can save the amount of energy to the minimum. So we can do all different kind of things to include using the, yes?
So I didn't understand this. Does plan B1 and B2, those are both provided by
It's
the user or
prepared by the system.
the system from the query, the single query B,
Right.
the system is able to
Right.
derive both plans
Right.
B1 and B2.
Right. If you remember the context translation map, that's prepared by the system. So that should be configured by external expertise, right? So eventually what we should do is to have a kind of ontology thing which probably exists in the internet, so that we can collect all the knowledge from different people, so that it can be imported to the system and use that as an extension of the map. So this shows the overall architecture of the Orchestrator. So we have APIs and application broker, and we have planning part, processing planning part. We have resource monitor, which monitors system resource in the background, and we have policy manager, plan generator, and plan selector. This is the part for the processing and feature extraction and recognizer. And the sensor part, the sensor broker part, is the part where it's communicate with the sensor. Also in the sensor side, we use TinyOS in this version, and on top of TinyOS we have resource monitor. So the sensor itself monitors resources including CPU and memory and also energy, and communicates through the mobile broker with the mobile side orchestrator, so that that orchestrator can do the orchestration. Also, the plan processor on the sensor side makes it possible to participate in the processing part if it is requested as such. For the communication protocols, we have developed a suite of protocols, including sensor detection protocol, sensor reporting protocol, and controlling protocol, and data reporting protocols. Okay, so this provides infrastructure to develop a kind of micro distributed system around a mobile device dynamically. So we tested with about less than around 10 sensors, many of them on body, some in the environment. I will just go very briefly. So to show the performance of the system, this was different from just simply showing the throughput or response time, because so we should have shown it works under a different environment, in the dynamic, changing environment. So what my student did was to simulate the changing environment. What they did was that they divided the timeline into 4 different phases. And in the first phase, they controlled the number of available sensors to 0 to 2. And in the second phase, they controlled it to 2 to 4, and 4 to 6, and 6 and 8. And again, every probably 2.5 minutes, they changed the number. So every 2.5 minutes, they increased 1 or decreased 1. But the total number was controlled in this range. Okay? And also, they did similar thing with number of requests from the applications. So they controlled in different phases between the number of queries between 0.5, 5 to 10, 10 to 15, and 15 to 20. Right? And that shows the workload. So it shows the result. So this is phase A, B, and C, and D. So in phase A and B, so here, in this case, is the number of query was fixed to 20, and we tried to see number of activated queries and number of activated sensors. Right? And in phase A and B, Orchestrator supported much more number of requests with a little bit less number of sensors. Right? And in phase C and D, again, it could fill up all the requests, but the other case was less than that, and still the number of sensors was very controlled very tightly. Okay? So on average, energy consumption was, because it used less sensor, was controlled a little bit lower, but the number of active queries was almost doubled. Okay? And similar thing was observed when we controlled, when you fixed the number of sensors to 6 and looked at the same thing. And again, what's confusing here is that in this case, this color shows our system performance. Okay? So it's, again, about half of the sensors. Even if we have 6, we have to control it less and show the performance of the supported queries similar. So that's, in a very high level, what we have. In the background, we have an infrastructure for monitoring the system and both sensor part and mobile part. And we also have sensor generation part, sensor detection part, and policy. All those things are regular system thing, and actually it's getting larger system now, and we are extending still toward into a larger scale. This, yeah.
3-4 minutes left.
Yes, right. That's enough. I wanted to show video, but I will skip it. The second part. So we have mobile device, okay? And it should be really mobile, support mobile thing. Right? It's not, because, for example, let's assume that you are running. Let's assume that you are coming to work and you get a phone call. And you should stop and push out your phone. And at the minimum, you should touch 5 times. you should push this button and touch probably 5 or 6 times. And think about you are jogging and you are listening to music and you want to skip to the next music. You should first stop and touch at around 10 times. You don't want to do it. So the mobile device should really support mobile situation, but it's not, because it's due to the limited interfaces. Right? So now Microsoft is doing gesture or voice to interact with mobiles without much attention. So this work is about developing mobile gesture interaction platform. Okay? Again, it's a platform. So we want to support application developers. They don't want to spend time in developing the detailed complex logics and care about the systems. Okay? So by providing this platform, the developers can develop their own application, interactions rather easily. The problem in that case was, again, energy. And in this case, one of the problems was the gesture recognition accuracy. Okay? The energy is natural. In this case, because we don't want to hold the phone, we put it into the pocket and we use wrist watch style sensor node. Okay? So that requires more energy. And what's interesting is that a lot of people worked on gesture recognition. However, in mobile situations, they say mobile, but in reality, they did in nomadic situations. So all their experiment was that then you move and stop and do the gesture and experiment and you move again. Right? So we wanted to do real mobile experiment. Right? So these are the two things we have done. So what we did was that one thing for the energy problem, what we did was that we used collaborative architecture. We developed an architecture where two devices, the sensor and mobile node, collaborate to save energy. And the second is the sensor node itself uses two different sensors, gyro and accelerometer, but in a clever way so here these two sensors have very different characteristics. Gyro is very good for motion, gesture recognition. However, it requires a lot of energy. So instead of using the gyro all the time, we have accelerometer in the front. Okay? This is cheap, but the accuracy is bad in mobile situation. Okay? So it is not robust to the mobility errors. Right? So what we did was we put this one in front of that and made a feedback loop between the two. So on this part, it does the segmentation, but in an adaptive way by having this control, closed control loop. Okay? So in that way, we can achieve the same accuracy level of the gyro provides, and the energy is saved much using this accelerometer. So what it does is gyro makes the accelerometer adaptive to the noise, the mobility noise situation. Okay? So by that, we could save the energy on the sensor node about 2.4 times. Okay? And the energy on the mobile side was reduced about this much, 43%. One interesting thing here is that the energy saving here is due to the segmentation done on the sensor node. Okay? The reason for that is, say, segmentation identifies the potential segment of gestures. So what it does is that rather than sending all the sense data to the mobile node, it sends chunk of data. And the interesting thing is that human gesture interaction is sporadic. Right? You don't do the gesture input all the time. You do it for a while and don't, and do it for a while and don't. So that data sending behavior is chunked, right? So for the other times, the mobile device can go to lower power sleep mode more easily, right? And that's the big issue in energy in this environment. So this could achieve a lot of savings. So in that way, I mean, I should stop here. So in that way, we could solve that problem of energy and the accuracy as well. But there is some more optimization which they've gone through to deal with the different mobility situations. So here in this experiment, we did a mobility experiment on the standing position and walking position and running position and the situation in a car. So we picked up those 4 cases as representative mobility situations, and we could achieve about 96% of accuracy, which is good enough in this kind of rather coarse level gesture interactions. But we should add more to cope with rather final level thing. But so far we could do this kind of remote control type of thing, like you run, you have a phone call, then you if you want to receive the phone while you are running, you do this gesture, and if you don't want to receive the phone, then do this. If you do this, then it's volume up, and if you do this, then it's volume less and volume down, and skip and go back. So this kind of gesture could be successfully implemented. So we implemented an application for MP3 player control while in running or walking situation. But we are doing further extending the system toward different applications and different things. So those are a bit of our mobile platform to support developers and users as well in 2 levels. One is the context monitoring level, and another was the interaction level. Okay. So I will stop here.
Thank you.